An important part for the modeling of a wireless power transfer is the model for the transformer that's used, or the coupled inductors. How to model the coupled inductors in a wireless power transfer system, especially a resonant wireless power transfer system. So what I'm going to do is, number one, I'm going to explain the model for coupled inductors that are tightly coupled. Okay, then we're going to discuss the modeling of loosely coupled inductors. Usually, tightly coupled inductors are in power inductors. Essentially, the primary and secondary coil are placed beside each other, or essentially in a very tight space, or even on top of each other on the same core, around the same core material. On the other hand, for loosely coupled inductors, this is typically what happens in a wireless power transfer system. You have the primary side, or the transmitting coil, is at a different orientation, maybe further away from the receiving coil, essentially, and so they are loosely coupled. So starting with the modeling of tightly coupled inductors. Well, first of all, if we get a pen or a pencil, or two pencils actually, and we get a copper wire, and then wound it around the first pin, and we get another one, copper essentially wire, and wound it on the second one. We have two coils, L1 and L2. Then if we apply AC voltage V1 across a coil 1, and we place both coils close to each other, what we'll find is, if we measure the voltage across the secondary coil, or coil 2, and we look at the waveform of V2 in an oscilloscope, for example, we will find that essentially the voltage V2 is going to be assigned just like V1. So let's put it here. If this is V1, we'll find V2 has the same waveform, however a different amplitude, such that the amplitude of V2 divided by the amplitude of V1 is equal to the number of turns of coil 2 divided by the number of turns for coil 1. Okay, and similarly, we have current going into L1 and current coming out of L2, assuming we have some kind of an equivalent resistance here to take some current. We will find that the ratio between I2 divided by I1 will have the reciprocal ratio of the voltage transformation ratio. So essentially it will be N1 over N2 rather than N2 over N1. And so if we calculate the power going here, P2, and the power taken here, P1, so P1 will be equal to V1 times I1, while P2 will equal to V2 times I2. And V2, if we replace V2 from this relation, we'll find it equal to N2 divided by N1 times V1. And then if we replace I2 from this equation, we'll find it equal to I1 times N1 over N2. So N1 cancels the denominator, N2 and N2 cancel out, and we find that P2 is equal to V1 times I1, which is equal to P1. So the power that's transmitted here will equal to the power that's received on coil 2, which makes sense. This is under ideal condition, where are no losses essentially, no resistive losses or no lossy components, assuming lossless components. Okay. So always remember the voltage transformation ratio is equal to the turns ratio of L2 to L1, and the current transformation on the other hand is the reciprocal of the voltage transformation ratio. Now transformers are, or the way you wound this the copper coil, you can wound it this way or you can wound it the other way. So you can do this or you can do the other way, right? So depending on the way you wound the coil, the voltage polarity of V2 with respect to V1, it could be in phase or opposite phase. Okay. So in order to accommodate this way of how you wound the coil around the core, we use dot convention. And the dot convention says that if this is a symbol for the coupled inductors or the transformer essentially, we're going to use a dot to indicate how the coil is rolled, or sorry, is wound around the core. And this means in the schematic, if V1 is positive at the dot, then the produced voltage will have a positive polarity at the dot of the secondary. So V2 will have positive polarity at the dot. So if this is the transformer, on the other hand, the dot of the secondary at the bottom, and this is V1, then the produced V2 will have positive polarity at the dot, at the bottom, instead of the top. On the other hand, if the current of the primary is entering the dot, then the current of the secondary should be leaving the dot. Similarly, if the current here is entering the dot, then the current of the secondary should be leaving via the dot. So let's make a simple exercise here. Let's say we select the voltage polarity as shown here, V1, and this is V2. The current I1 is entering the dot. However, we select I2 to be also entering the dot instead of leaving the dot. In this case, we'll find that I2 over I1, we should accommodate and add a minus sign basically. So it will be minus N1 over N2. So still, I2 over I1 is N1 over N2, which is the reciprocal of the turns ratio. However, we just need to add a minus sign since the reference direction or the positive direction of the current should be leaving the dot instead of the secondary instead of entering the dot. Let's look at the bottom case. So in the bottom case, essentially V1 and V2, I1 is entering the dot and I2 is leaving the dot, so that's the typical direction or the reference direction, or how the current will actually behave. The positive current will behave or flow in the secondary is going to leave the dot. So essentially we will have positive N1 over N2 rather than minus N1 over N2. Now let's look in this case, we have V1 positive polarity at the dot. However, V2 we assume to have a negative polarity at the dot. So in this case, V2 over V1 to accommodate the negative direction, or essentially the negative polarity, because we know that the rule says the voltage that will be produced at the secondary will have a positive polarity at the dot, not negative polarity. So we have to add a minus sign to the voltage transformation ratio. Okay. Now, in this case at the bottom, we find that the current at the primary is entering the dot, while the current in the secondary is entering also the dot rather than leaving. Similarly, the secondary voltage has a minus sign at the dot instead of positive. Then we have to add a minus sign in the voltage transformation ratio, as well as a minus sign in the current transformation ratio. Now, the turns ratio obviously is the we can say it n small, which is the number of turns for the coil 2 N2 divided by the number of turns for coil 1. This is also is equal to square root L2 over L1, the inductance, the self-inductance of coil 2 divided by the self-inductance of coil 1, just take the square root 2. Another point to remember is that we said V2 divided by V1, the voltage transformation ratio is equal to N. The current transformation ratio is equal to 1 over N. So this is 1 to N, where N is given by is the turns ratio. What about Z2 divided by Z1? So essentially, Z2 divided by Z2, Z2 divided by Z1, this is Z2. What is Z1? Z1 is basically the equivalent impedance seen looking through the primary side of the transformer. What is the impedance, the equivalent impedance of Z2 as we see it from the primary side or through the primary side? Because at the end of the day, Z1 is equal to what? The ratio between V1 divided by I1. You have a current flowing here in the primary side as well as you have voltage applied. So the ratio between the voltage and current is going to give you the impedance. Okay, and so Z1 represents the equivalent impedance of Z2 as seen through the primary side. And to find this ratio, you will find it at the end of the day equal to N squared. So it's exactly similar to the voltage transformation, just take the square. And why is that? Well, V1 is equal to what? From this equation is equal to V2 divided by N. What about I1? Well, I1 from this equation is equal to N times I2. So this will give us 1 over N squared, then multiplied by V2 over I2. Well, if this is V2 and this is the current, the ratio is basically Z2. So this will be equal to Z2 divided by N squared. And so if Z1 is equal to Z2 divided by N squared, this means that Z2 divided by Z1 is equal to N squared, as I mentioned at the beginning. So these are the three equations that govern an ideal transformer. Now, another point about impedance transformation, or moving the impedance from the primary to the secondary side or from the secondary to the primary side. So we said if we have an impedance at the secondary side, or let's start by this one. If we have an impedance on the secondary side that's connected across the secondary transformer or coil 2, we can move it to the primary side, or will be seen on the primary side as an impedance equal to, remember, Z2 divided by Z1 is equal to N squared. And so if in this case we have essentially want Zx as seen from the primary side divided by Zx will equal to 1 over N squared. And so this means Zx1 would equal to Zx divided by N squared. And the new point here that we should be careful about is if the impedance on the secondary side that we want to move to the primary side is connected in parallel with L2, then it should be transformed to the primary side in parallel. On the other hand, if it's connected in series with the secondary coil, then when we transform it to the primary side, we should also connect it in series. And again, it will be Zx over N squared. So in both cases, it's Zx over N squared. However, in case 1, it was in parallel with L2, so we transfer it to L in parallel with L1. In case 2, it was in series with the secondary coil, so when we transform it to the primary side, we transform it in series or connected in series in the primary side. And similarly, if we have an impedance on the primary side and want to move it to or find its equivalent or move it to the secondary side or find its equivalent impedance as seen via the secondary side, is going to be, as we know, Z2 over Z1 is equal to n squared. So all we need to do is just multiply Z1 by n squared and move it to the secondary side. And since it's in series with the primary, then it has to be connected in series with the secondary. On the other hand, for case 2, Z1 is on the primary side but connected in parallel with the primary coil. So when we move it to the secondary side, we should connect it in parallel with the secondary coil, and of course its value is the same thing, n squared times Z1.